Computing the 50th Fibonacci number, the obvious way, the clean little recursive function everyone writes, makes about 25 billion function calls and takes minutes. Computing it the smart way makes 50 calls and finishes before you blink. Same formula, same answer, a billion-fold difference. That gap has a name, dynamic programming. And it's the reason so many people think DP is the hardest thing in coding interviews. Here's the secret that makes it easy. Dynamic programming is not some clever trick you have to invent. It's just recursion that refuses to do the same work twice. That obvious recursive Fibonacci is slow for one reason. It computes the same sub-answers over and over billions of times. The instant you see that repeated work, the fix is obvious, and every dynamic programming problem on Earth becomes the same two moves. So forget the scary definitions. In the next few minutes, you're going to watch the repeated work appear. Watch us kill it, and walk away able to spot a DP problem in an interview in about 10 seconds. Let's go. Let's actually look at why that recursive Fibonacci is so slow. Because the picture is the whole lesson. Fibonacci of n is Fibonacci of n-1 plus Fibonacci of n-2. So to compute fib of 5, you compute fib of 4 and fib of 3. Fib of 4 computes fib of 3 and fib of 2. And here's the disaster. Fib of 3 just got computed twice, once on its own, once inside fib of 4. Go one level deeper and fib of 2 gets computed 3 times. Draw the full recursion tree and it explodes. The same handful of subproblems recomputed exponentially many times. That is the entire villain of the story. The technical name is overlapping subproblems. The recursion keeps asking the same question and paying full price for the answer every single time. And that word, overlapping, is your detector. Anytime a brute force recursion solves the same smaller problem again and again, you are looking at a dynamic programming problem, and the exponential blow-up is pure waste because the answer never changes. Fib of 3 is always 2, so don't compute it twice. That's it. That's the whole idea. Everything else is just how you avoid the repeat. So how do we stop paying twice? The simplest fix, and the one that barely changes your code, memoization. You keep that natural recursive function exactly as it is, and you add one thing, a cache, a little notebook. Before you compute fib of some number, you check the notebook. Have I already solved this? If yes, return the stored answer instantly. If no, compute it once, write it in the notebook, and return it. Watch what that does to the exploding tree. The first time you reach fib of 3, you compute it for real. But every other time that branch appears, you hit the cache and stop dead. The whole right side of the tree just vanishes. You go from 25 billion calls to about 50, because each subproblem is now solved exactly once. This is called top-down, because you start from the big problem, fib of 50, and let the recursion break it down, caching on the way. The beauty of memoization is you barely think, write the obvious recursion, add a cache keyed on the arguments, done. In an interview, this is often the fastest path to a correct, efficient answer. Solve it recursively, then say, and I'll memoize this to kill the repeated subproblems. That sentence alone signals you know exactly what's happening. There's a second way to kill the repeated work, and interviewers love when you can do both. Tabulation or bottom up. Instead of starting at the top and recursing down, you flip it. Start from the smallest subproblems and build up to the answer, filling a table as you go. For Fibonacci, you make an array. Write the base cases in the first 2 slots. Fib of 0 is 0, fib of 1 is 1, and then just walk forward. Each slot is the sum of the 2 before it. Slot by slot, the table fills, left to right, until the answer you want is sitting in the last cell. No recursion, no call stack, no cache misses, just a loop filling an array. Watch it fill. Every value is computed exactly once, in an order that guarantees the pieces it needs are already there when it arrives. That's the key insight of bottom-up. You choose an order so that by the time you compute a cell, its dependencies are done. Memoization and tabulation compute the exact same values the same number of times. They just differ in direction. Top-down, recurses and caches, bottom-up loops and fills. Top-down is easier to write. Bottom-up avoids recursion overhead and makes the next trick, saving memory, obvious. Here's the part that turns dynamic programming from "I hope I get it" into a procedure you can run on any problem. 4 steps every time. 1. Define the state. What's the smallest set of variables that describes a subproblem? For Fibonacci, it's just the index n. This is the hardest and most important step. Get the state right, and the rest falls out. 2. Write the recurrence. How does the answer for one state depend on smaller states? Fib of n equals fib of n minus 1 plus fib of n minus 2. 3. Pick the order. Top-down with memoization, or bottom-up filling a table. Decide which direction makes the dependencies available when you need them. 4. Nail the base cases. The smallest states you can answer directly, with no recursion. That's the whole method. State, recurrence, order, base case. When an interviewer gives you a DP problem, don't stare at it, hoping for inspiration. Literally, walk these 4 steps out loud. 90% of the difficulty is step 1, defining the state, and the other 3 are almost mechanical once you have it. The skill that actually wins interviews isn't solving dynamic programming. It's recognizing it fast, so you don't waste 10 minutes on a greedy approach that falls apart. 3 tells. First, the problem asks for an optimum or a count, the maximum profit, the minimum number of coins, the longest subsequence, the number of ways to do something. Best, or how many, is a giant flashing DP sign. Second, at each step, you make a choice. Take this item or skip it. Use this coin or that one. And choices lead to more choices. Third, and decisive. Those choices produce overlapping sub-problems. Different paths end up needing the same sub-answer. Optimum or count plus choices plus overlap. That's dynamic programming. And the fast litmus test? Try to describe a brute force recursion. If that recursion would obviously recompute the same thing, you've found your DP, and you're already halfway to the answer because the recursion is your recurrence. Say that out loud in an interview, and you look like you've done 100 of these. Here's the reassuring part. The dynamic programming questions you'll actually face collapse into a small handful of recurring shapes, and once you know them, new problems look familiar. 0-1 knapsack. For each item, take it or leave it, under a capacity limit. The ancestor of a huge family of choose a subset problems. Subsequence problems, longest increasing subsequence, longest common subsequence between 2 strings, the workhorses of string DP, coin change, minimum coins, or number of ways to make an amount, the classic unbounded choice, edit distance, the minimum edits to turn one string into another, the thing behind spell checkers and diff tools, and grid dynamic programming, paths and costs through a 2-dimensional grid. You do not need to memorize dozens of problems. You need to recognize which of these 5 or 6 shapes a new problem is wearing, because the state and recurrence come straight from the pattern. That's the whole promise of pattern-first prep. Stop grinding random problems. Start recognizing structures. Let's make the jump to 2 dimensions, because that's where people freeze. And it's the same idea with one more variable. Classic problem. You're at the top left of a grid. You can only move right or down. How many distinct paths reach the bottom right? Brute force recursion explodes again. Tons of paths share the same subpaths. So, the state is your position, row I and column J. The recurrence. The number of ways to reach a cell is the ways to reach the cell above it, plus the ways to reach the cell to its left, because those are the only 2 ways in. The base case. The entire top row and left column have exactly one path. You just go straight. Now watch the table fill. Start at the top left, sweep across each row, and every cell is simply the sum of the one above and the one to its left. The number in the bottom right corner is your answer. That's 2-dimensional dynamic programming. A grid of subproblems filling in an order where every cell's dependencies are already computed. Same 4 steps, same fill, so the pieces are ready. Just a table instead of a line. Here's the move that makes an interviewer nod. Look at that grid filling. When you compute a cell, you only ever look at the row above and the cell to the left. You never touch anything from 2 rows back. So why are you storing the whole grid? You don't have to. You can keep just the previous row, or often a single rolling array, and overwrite as you go, dropping the memory from the full table down to 1 row. Same for 1-dimensional problems like Fibonacci. You only need the last 2 values, not the entire array. So the real smart Fibonacci uses constant memory. 2 variables. This is the classic follow-up. You give the clean table solution and then say, and I can optimize the space by keeping only the rows I actually depend on. The general principle: look at your recurrence, see how far back it reaches, and keep only that much. Getting the answer is the interview. Noticing you can shrink the memory is the senior interview. The traps that sink dynamic programming answers. 1. Jumping to code before defining the state. If you can't say in 1 sentence what a subproblem is, you're not ready to write the recurrence. 2. A wrong or greedy recurrence, assuming the locally best choice is globally best when the problem has overlapping subproblems. That's exactly when greedy fails and DP is required. 3. Botched base cases. Most dynamic programming bugs live here, in the smallest states and the boundaries of the table. 4. Wrong fill order in tabulation. Computing a cell before the cells it depends on are ready. 5. Memoizing on an incomplete key. Your cache key must capture every variable in the state, or you'll return a cached answer for the wrong subproblem. And 6. Grinding 200 problems instead of learning the 6 patterns. You'll see a new problem and panic instead of recognizing the shape. Learn to define state and spot overlap, and the panic disappears. So, dynamic programming is not hard. It's recursion that refuses to repeat itself. The villain is always the same: overlapping subproblems, the recursion computing the same answer over and over. You kill it 2 ways: memoization, top-down, cache as you recurse, or tabulation, bottom-up, fill a table in dependency order. You solve any DP problem with 1 4-step framework. Define the state, write the recurrence, pick the order, set the base cases, and 90% of the work is nailing the state. You spot dynamic programming by 3 tells. It asks for an optimum or a count, you make choices, and those choices overlap. Almost everything you'll face is one of a few shapes: knapsack, subsequences, coin change, edit distance, grid. And the senior flourish is shrinking the memory to just the rows your recurrence reaches back to. Learn to see the repeated work, and dynamic programming stops being the scary one. If you want to practice this with an interviewer that pushes back and makes you defend your state and recurrence out loud, that's exactly what we built, free at crackit.io. Pick a pattern, solve it, then go defend it. See you in the next one.